Welcome to an economic architecture review of decentralized AI. Based on the framework from Own Your Mind, we are cutting through the marketing hype to look at the mathematical reality of why crypto and artificial intelligence are converging. Today, the standard AI model is entirely centralized. Your data flows into corporate servers to train massive models, which inevitably creates a bottleneck. A single intermediary controls access, extracts heavy rent, and holds the power to censor the output. If you try to decentralize this without a coordination mechanism, you get chaos. Thousands of isolated, disconnected terminals failing to synchronize the massive, complex workloads required for machine learning. Decentralized AI offers an alternative to corporate monopolies, but it introduces a massive obstacle: coordinating independent, untrusting actors at a global scale. The physical foundation of this system requires compute providers. These independent operators supply the raw GPU processing power needed to train the models. Then you need data contributors, validators to ensure quality control, and model builders to maintain code. Each role requires specific, reliable incentives. Cryptographic tokens function as the programmable coordination layer for this system. They replace central intermediaries with code, establishing the trust necessary to align these distinct actors toward a single objective. Every decentralized network faces the exact same paradox. You cannot attract compute providers to your network if there are no users paying for the service, and you cannot attract users if there is no compute capacity available. Traditional software companies solve this cold start problem with cash. They spend massive amounts of fiat currency on customer acquisition cost, hoping to slowly recover the lifetime value of that user over several years. This equation shows how token networks rewrite the formula. They transform customer acquisition cost into programmatic token emissions, paying early providers with future network value. By shifting to this model, the token actively links four vital components of the network architecture. First, incentives become programmable. You can write code that explicitly dictates what behaviors earn rewards, like providing data or verifying work, without relying on arbitrary corporate policy. Second, verification becomes cryptographic. Mechanisms like stake slashing and mathematical proofs confirm work was actually done. You don't need a team of lawyers to enforce a contract. The code enforces itself. Third, the system creates automatic alignment. Early contributors, developers, and active users hold the native asset, so everyone shares in the financial upside if the network succeeds. But there is a massive catch. Paying participants in future value only works if the token actually appreciates, and more importantly, if those early recipients don't immediately dump their assets on the open market. Token emissions are a brilliant temporary bootstrap mechanism to survive the brutal phase before a network finds product-market fit. But structurally, they are highly vulnerable to insider manipulation. To see how a network attempts to neutralize that manipulation, we look at Morpheus. Structurally, it is the clearest example we have of a decentralized fair launch. The core premise of a true fair launch is zero insider allocation. There was no pre-mine. Every single Morpheus token in existence had to be earned through active, provable contribution to the network. This chart breaks down their four-contributor economic model, assigning exactly 24% of rewards to compute providers, code builders, capital providers, and the community fund. Over time, that distribution follows a 16-year emission decay curve, ensuring late entrants aren't left subsidizing the earliest participants. Notice the capital provider role. Instead of handing cash to founders, they stake specific assets, like Ethereum, funding the protocol's ongoing development. Compare this to your typical venture-backed crypto launch. Insiders usually secure 20 to 40% of the supply at a fraction of a penny. Once the token lists, they dump those assets on retail investors, stalling the network. Because Morpheus eliminates this dynamic, it scores a highly respectable 76 out of 100 on the Freedom Score framework. But that ideological purity comes with severe operational drawbacks. Without market makers seated with initial supply, the network suffers from terrible liquidity.
The daily trading volume is incredibly thin, creating massive slippage that makes large transactions highly impractical for a serious enterprise. Fair launches successfully fix the broken wealth distribution of early token networks. The Gini coefficient starts low and stays healthy, but they cannot artificially generate the deep liquidity required to function as a reliable enterprise payment rail. Once the initial bootstrap phase concludes, the focus shifts to longevity. When token emissions inevitably dry up, the network must rely on a different source of fundamental value to sustain its participants. We measure this using the return score framework, evaluating specific dimensions like value accrual, revenue sustainability, and supply dynamics. Take Bittensor, for example. It is the largest decentralized AI network by market cap, boasting over 128 competitive subnets routing real workloads. But mapping this incentive structure reveals a misalignment. Sheer wealth dictates tau earnings more than actual AI quality, the stake-weight problem. Furthermore, Bittensor relies entirely on native emissions. Generating zero external revenue, it lands a dismal 6 out of 25 for revenue sustainability. Or look at Fetch.ai and the ASI Alliance. They serve as a perfect case study for why combining multiple struggling projects into a single token merger does not magically generate network value. Following their highly publicized merger, the project faced legal disputes over undisclosed token sales, and the asset's price crashed 96% from its all-time high. They attempted to introduce an earn and burn mechanism to restore value, but destroying a token only improves the economics if the volume burned is actually meaningful compared to the network's inflation rate. The initial fetch burn removed just 0.18% of the total supply. Mathematically, it had virtually zero economic impact. There is a strict divide here. Legitimate value accrual comes from taking real external customer revenue and using it to permanently buy back and burn tokens. Illegitimate accrual is when a network forces users to burn tokens for registration, only to recycle them straight back into the emission pool. If the only reason to stake an asset is to earn more of that exact same asset, with no external money entering the system, it is just a slow-motion Ponzi scheme. Every early-stage decentralized AI project is currently sprinting toward a single point of failure, the sustainability cliff. The cliff is the exact moment token emissions halve or decay to zero entirely. That is when the subsidy paying for network security vanishes. At this intersection, projects split into two paths: upward toward external revenue or downward to collapse. On the green path, you find networks like Akash and Venice. They survived the cliff because they have real, external customers paying actual fiat or stablecoins for measurable computing power and API usage. On the red path are the networks strictly dependent on their own inflation. If your entire architecture relies on printing new tokens to pay your compute providers, what happens to those providers the day the rewards stop? Token emissions are simply a customer acquisition cost. They are not true revenue. Any project that confuses the two will inevitably collapse. So how do investors and architects evaluate if a token is a genuine innovation or a useless wrapper? You apply the token necessity test. A token is a wrapper if the project could theoretically strip away its native asset tomorrow and just operate as a traditional software company using USDC or fiat currency. A token is essential when the network's core functions, like trustless settlement, competitive routing, and complex multi-party rewards, are structurally impossible to execute without native programmability. The test is simple. If attempting to run the exact same protocol as a centralized corporation would require an army of lawyers, thousands of contracts, and a massive payroll department, then the cryptographic token is genuinely necessary. This is why these two technologies are converging. Artificial intelligence demands computing coordination at a massive global scale. Cryptographic tokens finally provide the trustless rails to organize that hardware. But in the end, only the networks that successfully transition from printing emissions to capturing real revenue will survive to power it.